questions involving a function of one variable, a vector valued function of one variable. So here is what's known as a vector valued function of one variable. The variable's t. Here I've written it as what's known as an ordered double, but you can write it, say, as in the following form, in the I and j notation. And we're interested in the following values of t. Now remember, one point or one motivation for studying these vector valued functions is that they can do more things than traditional y equals f of x functions. And we're asked to do a few things with this vector valued function. We're asked to compute a tangent vector to the curve associated with r of t. We're asked to compute the speed of the particle. We're asked to compute some limits, in particular the limit of the velocity and the speed as t goes to 4 pi. And we're asked to compute the length of the curve which the particle travels over between the time instances 0 and 4 pi. Okay, so I've used Maple to actually plot the curve associated with this, this vector function. So here it is. The curve has a special name known as an involute of a circle. And one of the motivations for studying these kinds of curves and these vector functions arises in mechanical engineering. This curve is being used to model the profile of a gear wheel. Now, if you want to look up a little bit more on that, there are a few YouTube videos, Wikipedia, where you can actually get a little bit more information about how this is done. Now, hopefully you can see down here that the curve, the particle starts here, and as t increases, essentially you're moving away from the origin in a spiralling motion. Okay, and the the 2 here, the factor of 2, goes back to the starting point on the x-axis. It's 2 units along the positive x-axis. Okay? Okay, well, let's work through these questions one by one and see if we can solve each part. Part A. For each positive value of t, compute a tangent vector to the curve C. So in this setting, this would be your curve C. Okay, so the first thing you might know about this curve is that it's a smooth curve. Okay, it doesn't have any spikes or cusps on it. So for t positive, this curve is smooth. All right. Instead of directly computing the tangent vector, what I'm going to do is compute the velocity vector. And the velocity vector will be one of the tangent vectors in this case. So to form a velocity vector, we just differentiate this function by differentiating the component functions. So the velocity vector this will also be a tangent vector. Is just the derivative of this vector valued function. Okay, so by the dash I mean dr dt. So let's go to the component functions and differentiate them. See if I can squeeze it in. Okay, so I want to differentiate 2 bracket cosine t plus t sine t. Okay, well, I know cosine is going to go to negative sine. And if I differentiate t sine t, I can use the product rule. right? It's going to be something like sine t minus t cos t. So actually, for this part, you're going to get some cancellation. But I'll write it all down. Okay, so cos t is going to go to negative sine t. Then I'll use the product rule on here. Sorry, sine t goes to cos t. Okay, and if I look cancel, cancel, and I'm just left with t cosine t in here. Similarly with the next bracket, if I differentiate sine t, I'll get cosine t. If I differentiate minus t cosine t by the product rule again, I'm going to get something like this. So essentially, if I can just squeeze it in, I get some cancellation. And I'm going to get something like this. Okay, so note my answer is a vector. Okay? Now in part B, for each positive value of t, compute the speed of the particle. So essentially, I just want the magnitude or the length of that velocity vector that I've just calculated in part A. So by these two pairs of sort of parallel lines, I mean the magnitude or the length of a vector. So how do I find the length or the magnitude? I basically take the components, square each of them, add them together and take the square root. So if I square the components, add them and take the square root, I'll get something like the following. Now, can I simplify it? Well, I'm going to get a cosine squared and a sine squared and a common factor of 4t squared. So I can simplify in here, just using cosine squared plus sine squared equals 1. And because t is positive, I can just get the answer to t here. I don't have to worry about absolute value signs. Okay, so I haven't put all the details in there, but that's the rule I'm using. So the speed is 2t. You can see as t increases, the speed's going to increase also. Now, part C, what are the limiting behaviours, or what are the limits of the velocity and the speed as t approaches 4 pi? Okay. Well, let's look at the velocity first. Velocity vector is just given here. And what I want to do is take the limit as t approaches 4 pi. Okay? Now, how do I take limits? I just look at each component function and take the limit there and write the answer as a vector. Okay? So, let's look at the velocity function first, or the velocity vector, sorry. Okay. Well, what's this going to go to as t goes to 4 pi? Well, both of these are continuous functions, so I just take the limit of that and the limit of that and write my answer as a vector. So 2t goes to 8 pi. Cos t goes to 1. So I'll get this. And what about this? Well, 2t again goes to 8 pi, but sine t goes to 0. So this then is just 8 pi I. Again, my answer is a vector. Now the second part of this question asks me about the speed. Well, you can calculate the speed as t goes to 4 pi in two ways. You can either look at this vector and look at the magnitude of it, or we calculated the speed up here, it was 2t. So whichever one you want to use, this is going to, I'm going to use this one, or you could use that one and just write down 8 pi. But this one is going to go to 8 pi. So our answer is a number here, right? Because we're talking about speed. Now the last question, what is the length of the curve which the particle travels over between t equals 0 and t equals 4 pi? So what is the length of that curve? I haven't drawn the whole curve in, but what is the length of that curve? Well, we use our arc length formula. Okay, it's just the integral essentially of the speed between these numbers. So in this example, little a would be 0 and little b would be 4 pi. Now I've calculated the speed at any time t. It's up here, it's 2t. Okay, so I have a pretty simple integration. Okay, I'm integrating 2t, that's pretty easy. So I'm going to get something like 16 pi squared. So let me just highlight these things. Okay, so that's a basic example comprising lots of elements for a function of one variable. Now, just a couple of basic points to summarise. For smooth curves, C, with parameterization, R of t. Remember, when I talk about smooth curves, I mean R dash, the derivative of R, is continuous and never zero vector. Geometrically, we mean the curve has no spikes or cusps. Right, so just to summarise, the velocity vector is the derivative. And that derivative vector is also a tangent vector. To the curve. And it points in the direction of motion. Secondly, speed is just the magnitude of this derivative vector R dash. Now, I won't write this down, but for limits of vector functions, you take the limits in a component-wise fashion. And finally, the arc length. For a curve traced out between, say, t equals a and t equals b, is just the integral of this speed function.